So I'm just going to repeat what I said before. We're going to talk today about the high-level architectural decisions of the vProgs framework, how everything is structured. We currently have the repository split into five, actually it's 6 domains, because we also have a core domain where there are some types that all the different layers need, like what is a transaction, for example, and these kind of things. But it's a very minimal kind of layer that just binds general utilities that are just useful for all of the parts of the code. So the main domains that we have is the 6 ones that you see on the screen. So the first one is the storage layer, which concerns itself with disk access. So it provides interfaces and utilities to write data to your storage and to read it back. We have the state domain, which essentially contains all of the models and how data is laid out. So it means what kind of information is stored about a resource. How is this stuff serialized? So how do we turn this data into binary format so that it can be stored on the disk? Then we have the scheduling layer, which is essentially the orchestrator for providing access to that stored data efficiently to the CPU, so we can process transactions that mutate this state. Then we have the ZK domain, which is zero knowledge or proving domain, which contains all of the zero knowledge related source code, a small VM. The backend that actually does the proving and a lot of other ZK related things that we can maybe talk about later, or maybe in the next session, we will see. Then we have the L1 domain, which essentially contains types that we need some extensions. For example, some types that live in Kaspa are not compatible with zero knowledge VMs because they are not no standard. That's a term used in Rust to determine or to name code that is compatible with very low level machinery. So we had to wrap some types or introduce some helper methods that are currently not easily usable from the Kaspa upstream repository. And then we have the node domain, which is essentially the big orchestrator that just takes all of these different layers and puts them together into a useful binary that you can run and execute as a user. And the reason why we have split the repository into these layers is because we want to have a very modular architecture. We want to be able to change individual aspects of these low-level things without having to deal with side effects. Like a lot of DLT source code is very intertwined. So for example, if you want to schedule access to your resources, the scheduling has certain requirements for the storage, for example, in respect to caching, that some state that you just loaded and you need to write it back to disk, that you can have it in some specific cache, for example, so it can be loaded again, which makes all the code base very complicated. And we're kind of building the system more in a layered approach, in the same way as the ISO-OSI model is working, for example. It's like how the internet is working, for example. You have like very low-level protocols that are self-contained, that don't concern themselves what applications you actually build on them. Then you have additional layers that introduce additional complexity and additional features. There's also like the entirety of nature is built like that, right? Like you have atoms, the atoms make molecules, the molecules make molecular networks, the molecular networks build cells, and there's build organisms and so on. It's not that at some point an organism comes around and has to invent its own atom just to be able to exist. So this entire layered architecture essentially gives us a very nice and modular isolation of concerns, essentially. And the dependencies flow strictly downward. So that means that the storage doesn't know anything about the state. It just provides a way to store arbitrary data. The state doesn't need to know anything about the scheduling. The scheduling layer doesn't need to know anything about the zero knowledge part. The L1 related code doesn't know anything about the node, and so on. So all of the dependencies are essentially strictly downward facing. And I've been thinking about what we should talk about today. I was first thinking about starting at the bottom and really start kind of like building things from the bottom up. But since the storage layer is pretty low level stuff, I mean, it's essentially just a wrapper around the key value store. The key value store is how you traditionally store data in blockchain context. You have you can imagine that like a dictionary, essentially, where you have different entries where you can store information with a key that identifies your stored value, and then the value is just a serialized sequence of bytes. And I don't think that's super interesting. We can dive into that maybe in one of the next sessions, because there's also some interesting aspects there. We have, for example, been able to develop a storage model where we don't need to wait for f-sync boundaries or well flashes or something. Like for the people who are maybe a little bit more into coding, they know more about what that means. But it's essentially we are able to stream data to the disk without having to wait for the disk to finish writing the data. So I think it's an interesting topic, but it's something that I would maybe exclude today just to get a better kind of like high level picture. So the first thing that I want to talk a little bit about is actually the state layer. And I've just depicted here A, B, C, D, and it's supposed to represent resources, because the way Kaspa and the vProgs framework models data is that we have individually addressable resources. Like in Ethereum, for example, the state is not very fine-grained. In theory, it is, but it's not addressable easily from the outside. So if you have, for example, the ERC20 token or something, then all the balances live in one storage account, and you cannot really, from the outside, from the scheduling layer, address individual accounts. So in this model, we have essentially state is just an object that is identifiable. So we have like just a letter A here denoting resource A, a letter B denoting resource B, C, D, and so on. And you can essentially imagine that that each coin, each balance, each little storage object that exists in the system is its own little object. And the ability to access and address these objects from the outside gives us the ability to then later parallelize the workload and get more scalability out of the system than what is, for example, possible in Ethereum. So let's talk a little bit about the scheduling layer. So just as a summary, so imagine just A is like a certain coin, a balance of a certain coin, B is another balance of a certain coin, and so on, right? So now the task of the scheduling layer is to allow us to process transactions which are coming from the L1. I've depicted this here as a little box with a badge. The badge is just the name that we use for a sequence of transactions that we received from the L1. So this is traditionally a chain block, including its merge set, but it doesn't contain all of the transaction. It contains the transaction that are filtered by a lane. So that means that if you are posting L2 transactions on Kaspa, then you can provide in your transaction a subnetwork ID, which translates to a lane identifier. So the L2 doesn't need to process all of the transactions, but it can only process the transactions that are ultimately relevant for its own processing. So here we have this queue of transactions of batch one, which are coming in. And it's just a very naive list of transactions that we have. And our goal is to ultimately process these transactions as fast and as efficient and, most importantly, as parallel as possible, right? And the first thing that we do to allow this to work is we introduce a little metadata field to each transaction where we say what we want to read and what we want to write. So this transaction, for example, says I want to read the object A, I want to write to resource B. This transaction 2 wants to read A, transaction 3 wants to write C, and so on, right? Like this can be just arbitrary resources that you want to access, but every transaction ultimately needs to name the resources that it wants to touch. This model is ultimately very similar to what Solana is doing, where you have essentially pre-declared dependencies, and those dependencies will then allow us to get more parallelism out of the entire system. So here we're going with a design that is very similar to the way Solana and, for example, also Zui are treating these kind of things, right? And the a second, what's the purpose of read-only transactions? Yeah, okay, that's just an example, because I need to kind of, I want to draw like and explain the scheduling mechanism. Usually, reading a transaction could, for example, be like, I don't know, you read an oracle or something, right? But traditionally, you pair that also with a write. So that means that you read an oracle and then you do something based on the value that you read. But this is just for me now. I mean, you will see in the next steps how this develops, just to understand how the entire scheduling works. So it's just a, how do you say? I'm not a native speaker, but it's just a made up workload, right? So, and the reason why or what the scheduler needs to achieve is it wants to parallelize the workload as much as possible. But whenever there's two people that want to write the same thing, then they need to wait for each other. Like you need to honor the order. If you have two transactions that touch disjoint accounts, like for example, I send money to my grandma and you send money to your grandma and it's not the same coins, or it's not the same state that you're touching, then these can perfectly run in parallel. Um, and the way this is traditionally done is that you have relatively complex machinery to identify this parallelizability. You have, for example, block STM in other projects where you have optimistic execution, where you just execute everything in parallel. If you detect a conflict, then you just cancel the execution and just run it again. And if you still have conflicts, you just cancel it again and run it again until you eventually processed everything. In Solana, for example, there's a priority graph system where you kind of like pop the first transactions from the graph and then you try to find non-overlapping accounts and then you execute them. And we have actually taken a slightly different approach. We are actually taking the idea that let's have every resource have its own little blockchain kind of, or like its own lane. So I've depicted that here as like this line going up. We will fill that in within with the next step soon. So every single resource essentially has its own little tiny blockchain, and every time somebody wants to access that chain, we will use the information and build essentially a computational DAG over all the workload. So let's just do the first step. And let's put the first transaction here. Transaction 1 wants to read A. So we have, I don't know if that's visible, but I hope so. You have like little adapter like things here. So you have an input to the transaction, you read the value. Here is a W because you want to write it. And then also once the transaction is done, it outputs the very same resource again. So it says, okay, I read this value and I've written this value. Here also I'm trying to write this value and I've produced this value. So you essentially have this little input and output that goes into each individual transaction that essentially holds the effects that the transaction specifically saw. So it stores its input and it kind of holds a reference to its output. And you just take the transaction and you essentially just put it on the chains that it requested. Then the next transaction accordingly, so this one wants to read A, so it essentially attaches to the same chain. And this is just it's just an in-memory reference here. This is just a 8-byte pointer ultimately that points to the other transaction. So it's not like cryptographically committed or anything. It's just an organizational structure internally that we use to kind of do all of the scheduling. Then we have the next transaction that wants to write to C. We have the next transaction, it wants to read B, and it wants to write to A and C. And then we have transaction 5 that wants to write to the account B. Right, so, and this is relatively simple. You just iterate over all the transactions, you check the resources, you attach it to their chains, build these little references in memory, and then you're kind of done. Then you have this data structure. So once we have this data structure, the question is what happens now, right? So the thing that the scheduler does is like whenever we attach something to a chain that doesn't have a predecessor, then it requests the data from the disk and says, okay, please provide me with the current state of the resource A, B, C in this case. Then it loads them and provides it to this DAG. So here I've just, for the sake of explaining how it behaves, I'm just pretending that loading B takes longer than the other ones. So A and C are already available. And then what happens is that this transaction, because it attached to the predecessor, gets notified, okay, this value is available for you. Like you can read this value. And because it's a read-only value, there's a short circuit that its produced value immediately trickles through. So that means that if I only read a value, then I cannot change it. So the produced value is just the same. And then it carries on to the next one immediately, right? Like it's just does like plop, plop, plop. And as soon as a transaction has all of its dependencies green, so in this case, this is a transaction that has all of its dependencies available, it starts executing. So I've denoted this here through the color blue, right? So here, this one, for example, is also processing, but because it's a write access, it wants to write something back. We cannot just route it directly through. So the next one needs to wait. We need to actually wait for this transaction to finalize its execution. And then the next step, let's say this one becomes available. The transaction now has all of its dependencies green. It starts executing. The other one's finished, and they populate the inputs of the next transactions. And then they continue to execute. As soon as this one is available, the third input becomes available, and this one starts to execute, and this one starts to execute. And so now all of the transactions are running. Now let's for a moment consider the possibility that this transaction here takes a very long time to finish, to process. In a traditional blockchain and in other systems, this would mean that the entire batch would have to wait. So if there's another batch coming in after this transaction, then we cannot continue. We just need to wait. So you have a lot of idle times. Because all of these transactions ultimately run on different CPUs. So I don't know, depending on what hardware you have available, maybe like 8 cores or 16 cores or whatever. If there's only one transaction running, or in this case, two transactions running, then all of the other, say 16 or 6 cores are essentially idle and not doing anything, which is very wasteful. And that's also one of the reasons why blockchains currently have such a big scaling issue. Because the workload that you see in the real world is not very parallelizable. Because sometimes, yeah, I don't know, like you have some MEV opportunity. A lot of people try to interact with the same state, or they try to just snatch the same opportunity. So they cannot really process anything in the meantime. And it's also one of the reasons why a lot of the blockchains, when they have their benchmarks in the lab, they do like 64,000 TPS or something, because they test the maximum throughput. They just want to see, okay, if we drive this thing to the limit, everything is parallelizable. How fast can we eventually go? And in practice, this is usually the case, that there's at least some serialized fraction of the workload which is not parallelizable, where you ultimately have to wait. In our system, however, that's not necessarily the case. It depends a little bit also on the workload. But if we now have the situation where, for example, batch 2 comes in, where we have another transaction that tries to interact with state that is not part of the congested state, then this transaction will just naturally execute in parallel, right? Like we will immediately put it to its own resource. So all of these transactions can continue to flow through the system. And this kind of property is a really, really nice property that currently no other blockchain has in that way. And it's essentially a direct consequence of decoupling execution from block production. Because traditionally, if you produce a block and you want to execute all the transactions, you put certain commitments into that block, which attest to what actually happened in that block. But in our case, the commitments and the blocks are produced by the L1, and the L1 doesn't care at all about what we're doing here. So it will continue to push new batches and new blocks, even if we're currently slightly slower, which results in a situation where these new blocks, as long as they have some independent workload, will eventually amortize the waiting time or the idle time that you would traditionally have. And you can essentially continue to process without throughput degradation the same amount of transactions. So that's something I think is really exciting, because it's one of the first DLTs in the space that actually does this. It's not a completely new idea. Actually, a lot of AI systems like TensorFlow, CUDA graphs, like a lot of graphics programming and CPU-based programming is based on exactly these ideas. And for somebody who's maybe more interested in like some computer science terminology or something, the way or the scaling is called the Gustafson style scaling versus blockchains, which are traditionally constrained by Amdahl's law. So Amdahl's law essentially says that the amount of parallelizability that you have is constrained by the non-parallelizable workload that you have. Like just imagine, I don't know, you plan a dinner for your friends or something, and it's pretty clear that you can only eat the dinner after you've cooked it, right? So you need to wait for the food to be cooked before you can eat it. So you cannot like parallelize these tasks. They're just strictly dependent on each other. Let's see. I just want to see what the comments say. Yeah, that's true. Also, like we have reached the point where it's no longer possible to scale the performance of single core CPUs. Right, there's a very important notice here, because the only way to make this faster is essentially to have smaller transistors, and we've reached a nanometer scale limit for these hardware where you cannot make them small anymore. You will have crosstalk between the wires and these kind of things. So it's likely that CPUs are not going to get significantly faster than they are today. Maybe we will see some increase, but most of the scaling that is nowadays possible just with hardware is constrained to just doing more stuff in parallel, right? So this is a very future-proof design, which ultimately allows us to kind of execute as much as theoretically possible in parallel. And then um, the next step is, yeah, okay. So the next step is just everything is processed. So if we look at this a little bit faster, it looks a little bit like the water is flowing through a pipe, kind of, right? So it's we don't have any complex managers outside. The only manager that exists is really the one that builds this structure in the beginning, that just iterates over the transaction and attaches them together. And as soon as this data structure is built, everything is reactive. The transactions themselves notify the next one. So it's extremely simple in code, or relatively simple in code, because you don't have any locks, we don't have any mutexes, we don't need to wait artificially between the execution. Yes, so let's then talk a little bit also about the ZK stuff. I don't have any additional graphics or pictures for this, because it takes quite a while to actually draw this, so it doesn't look completely stupid, but I think we can anyway talk a little bit about this. So the way this execution works is that the scheduler takes a generic, so it's kind of like has like a placeholder contract, what happened, like what information it gets for each transaction execution, and what results it needs to produce. And then you can take any VM and just plug it in there. Like we have this shown that you can, for example, implement the Moog VM relatively early on when we didn't have the ZK proving capabilities yet. So what the ZK layer does is it defines a virtual machine for this scheduler, which essentially just plugs itself in at each of these boxes. And instead of just executing the transaction in the sense that we produce the state changes, it also produces journals about what happened. And it also fires off an eventual prover that lives on the side here. Like you could just imagine there's like a box on the side, because that's not part of the scheduler itself. You can, for example, offload proving to a proving network, or you can do it on another machine. And in fact, the entire architecture is designed in a way that you can parallelize it across as many machines as possible, because each of these transaction executions produces an individual proof. And the way we maintain and store this is that within our system, every transaction has a little, I don't know, looks like a little inbox, maybe. I don't know, where the proof then gets deposited. So as soon as a transaction is proven, you publish this transaction to this proof to the transaction, and the ZK layer just waits until all of these proofs exist for all the transaction, and then goes ahead and stitches them together to a batch level proof, so you can prove the entire execution of the entire batch. And then there's also gonna be, and it's something that we're currently building, an aggregation layer that takes multiple batches and then stitches them together to a settlement proof, which eventually lands on the L1. And yeah, we can look at that in much more detail also, maybe in the next session, but I will take some more time to produce some graphics and have some more details on that. And the way the entire system eventually closes is the L1 essentially ingests data and produces the batches that are pushed to the scheduler, right? It waits for the proving pipeline to produce the proofs, and then sends a transaction back to the L1 that essentially does the settlement. And that's where the Toccata hard fork comes into play, where we have the capability to have covenants, which essentially allow us to define conditions like that a state can only be advanced after producing a proof that attests to the effects that we have seen in the entire system. there's a lot more things that can and should be said, but I didn't want to cover everything in the first session, so I would kind of be done with this high-level overview. Is there any questions so far? Or anything that we should maybe address that I maybe missed? I don't know. What was it somehow understandable? Also, this entire scheduling part, because I think that's kind of the core of yeah, how everything that is not ZK related works. It's not too complicated. I mean, it's really just like building puzzle pieces, right? Like you have these little pieces, they click together, data flows through, and then you just execute. And I think the biggest amount of work, also just to summarize what we're working on, the biggest problem is really like how do you, I don't know, conceptualize the entire data flow in a way that it doesn't become a complete complexity clusterfuck, right? We don't want to build a system like Solana where single files have like, I don't know, 3,000, 4,000 lines. If we look at the code in the scheduler, for example, I think the biggest file by line count is like, I don't know, 100 lines or something. So this is ultimately really very little code, and it's also very efficient. And what we're just as a summary also, but we can just talk about this also maybe in the breakout session in a few moments and just discuss a lot of things, because there's so many things that we can talk about also in the general yeah, in general in respect to Kaspa and in respect to game theory and consensus protocols and these kind of things. But when it comes to vProgs, I think that's a kind of high level overview. So if there's not any concrete questions, then maybe I think it's time for beer and just let's hang out. I'll just wait like 2 minutes and see if anybody writes anything that is maybe unclear or something. Okay, it seems like people understood it. As I said, like we can take the following sessions to dive into concrete code, to look at the code, how everything is implemented, and you will see that it's actually relatively little code to get all of this done. Right. So now the question is, how do we do the hangout session? Should we just switch to some other room where everybody can speak, or should I just get everybody on the stage?